Hello, welcome to this brief presentation looking at methods of differentiation. There are mainly three methods of differentiating non-standard forms known as products, quotients and a function of functions. This presentation will only look at products. When I refer to products, I mean something like a function y equals 3x squared multiplied by sine x. This is a product, and both functions, the 3x squared and the sine x, are functions of x. I'm going to show the product rule here with no proof to save time on the presentation. So we're just going to look at applications of this product formula as given. So the product formula we'll be using throughout all the questions in this presentation is trying to find the first differential equation, dy by dx, of a function y. And to do this, the formula states we need to find a u term, a dv dx term, a v term and a du dx term. What you'll see in a moment is that from the expression we will state a u term and a v term from the information given in the question, and we will then have to find the du dx term and the dv dx term, and we will put all these four terms into the product formula and then rearrange. So I'm going to go through an example. Example 1 we're going to look at here. It says find the differential coefficient of, and this is the function we are given, y equals 3x squared times by the sine of 2x. This is the product because it's a function of x, i.e. 3x squared multiplied by another function of x, sine 2x. So given our equation, okay, we know it's a product because both terms are functions of x's. So I first of all have to define my u and my v term. So in this case I'm going to let my u be 3x squared, and I'm going to let my v term be sine 2x. It doesn't matter if you let the v term be 3x squared and the u term be sine 2x, it makes no difference. So I'm just going to take them as they are stated, u first and v second. So in this case u is equal to 3x squared and v is equal to sine x. And in every question we will start by defining a u and a v term from the equation given. We then need to work out the differential of u with respect to x. In this case 3x squared differentiated becomes 6x, and I'm getting that from standard differential tables. And if I differentiate the v term with respect to x, I will get 2 cos 2x, so differentiating sine 2x, again using the standard form there of sine ax, I get a cos ax, so in this case it's 2 cos 2x. Now I've got my four terms of u, v, du dx and dv dx. I now apply them into the product rule. So in this case my u term is 3x squared, my dv dx term is 2 cos 2x. I'm adding that to my v term, which in this case is sine 2x, and I'm multiplying that by my du dx term, which is 6x. The differentiation is effectively done now. The remaining two lines are all relate to simplification using algebraic manipulation. First term here, I'm multiplying the 3 by the 2 to give me 6x squared. Multiplying that by the cos 2x, that's my first term, and I'm adding to that, I just brought the 6x to the front of this expression and put the sine 2x behind it. This final line to find the differential dy by dx, all I've done is factorise on the highest common factor, which is 6x for the two terms, and that leaves me in the bracket x plus cos 2x plus sine 2x. So given the original equation of y equals 3x squared times by the sine of 2x, I now know the differential dy by dx is equal to 6x open bracket x cos 2x plus sine 2x close bracket. In the handout that we're using here, exercise 1 have 5 component parts to it, little questions, and I'm going to work through each of these questions in the same way as I have with the example 1. So here's exercise 1. It says differentiate in part A this function y equals x cubed times cos 3x. Again, I need to define, given the equation, my u term, which I'm saying is x cubed, define my v term, which I'm saying is cos 3x. I need to find the differential of u with respect to x, the du dx term, which from standard tables would be 3x squared. I need to find the differential of v with respect to x, dv dx, which again from standard tables, differential tables, would give me minus 3 sine 3x. I now apply my product formula. I put in the u term, which is x cubed in this case. I multiply that by the dv dx term, and then I add to that my v term, which is cos 3x, and I multiply that by my du dx term, which in this case is 3x squared. Again, differentiation effectively done now. It's all simplification. All I've done for this line is brought the minus 3 to the front of the equation and then multiplying it by x cubed sine 3x. And then I'm adding to it, I just brought the 3x squared term to the front of this part of the equation and the cos 3x afterwards. I'm looking for highest common factor, and that's 3x squared in this case. And then inside the bracket, notice here I've just brought the cos 3x function to the front and put the negative sine 3x function to the back. That's just a convention that if you have a positive and negative term, you put the positive term first. So it's cos 3x minus the x sine 3x in this case. Don't forget, you can always check your factorisation by expanding the brackets back, and you'll get back to the previous line. So again, I found my first differential, my dy dx of y equals x cubed cos 3x. Exercise 1 part B here, it says determine, and notice the short hand notation there, determine d by dx of e to the 2x sine 4x. So that's a shorthand notation of d by dx means differentiate. So I'm going to differentiate y equals e to the 2x sine 4x. Again, we can clearly see this as a product because it's two functions of x multiplied together, the e to the 2x times the sine 4x. Define my u term, u is equal to e to the 2x. Define my v term, v is equal to sine 4x. Differentiate my u with respect to x, I get 2e to the 2x, these are all standard forms again. Differentiate v with respect to x, I get 4 cos 4x, all standard forms from standard differential tables. Apply my product formula here, I put in my u term first of all, in this case is e to the 2x, multiply it by my dv dx term, the 4 cos 4x, and I add to it, add to it my sine 4x term, which is my v term, and I multiply that by my du dx term. So again, I'm just really filling in the equation, the product formula there. Again, a little bit of simplification. I brought the 4 to the front of the expression, so 4e to the 2x times cos 4x, and I'm adding to that and bringing the 2e to the 2x to the front and multiplying it by the sine 4x term. Again, final step here, I'm just factorising. Highest common factor for the two terms above is 2e to the 2x. So inside the bracket I will now get 2 cos 4x plus sine 4x. Again, if you expand the bracket, you'll get back to the previous line. So again, I found the dy by dx term. I found the first differential of the e to the 2x sine 4x function. Question 3 here, it says find the rate of change in this question, find the rate of change of y with respect to x. That essentially means differentiate. Don't forget, differential is all about rate of change. So when it says find the rate of change of y with respect to x, it's just saying differentiate. Again, it's giving me a function, y equals 3 times the square root of x times the ln x function, a natural log function 2x. So given the function, notice that the 3 times the square root of x can be written as 3x to the half using fractional index notation. Be aware of that. So 3 times the square root of x is actually 3 times x to the power of a half. So I'm letting my u equal to that. My v in this case will be the ln 2x. I now differentiate u with respect to x. if you follow the standard form through, that will give me 3 upon 2 times by x to the minus a half, or if you prefer 1.5 x to the minus 0.5. I'm going to keep mine as fractional index for now. When I differentiate my v with respect to x, I will get x to the minus 1. If you look in your standard tables, when you differentiate ln ax, ln 2x in this case, you always get x to the minus 1. Applying the product formula to find my dy by dx, the u in this case is 3x to the half, the dv dx in this case is x to the minus 1. Add to that my v term, which is ln 2x, and I multiply by my du dx term, which is 3 upon 2 times x to the minus a half. Again, just slightly simplifying here. Notice here I've got 3x to the minus a half, and that's because I'm using the law of indices to get this minus a half term at the top, because the first law of indices says if you've got x to the half multiplied by x to the minus 1, you add up the indice, so that's minus a half, so that becomes 3x to the minus a half, and I'm adding to that, and all I've done here is brought the 3 upon 2 x to the minus half in front of the ln 2x. Again, that's a convention in mathematics. I'm factorising on this line here. 3x to the minus a half is common to both terms if you look at them above. So in the brackets I will get 1 times 3x to the minus a half there plus a half of ln 2x. I've also written in terms of decimals. If some of you may have worked this through in decimals instead of fractions, you should end up with 3x to the minus a half open bracket 1 plus 0.5 ln 2x. Both for those last two lines mean exactly the same. Okay, exercise 1 part 4, has to differentiate this function y equals x cubed cos 3x times ln x. Notice there are 3 functions of x in this question. The x cubed is a function of x, the cos 3x is a function of x, and ln x function of x. They're all multiplied together. So what we've basically got here, you'll see in just a moment, is a product inside a product. So given that y is equal to x cubed cos 3x ln x, I'm going to let u in this case be the first 2 functions of x. So x cubed cos 3x, and I'll let v in a moment simply be the ln x term. So by making u the x cubed cos 3x, I've actually got a product. Okay, so I've got a product within a product. To actually work out the du dx in this case, I'm actually going to have to use the product formula. In all the previous examples, to work out the du dx, it was always a standard form function. We could just look it up in a table, but that's not the case here. So I've kind of got a local product to do, if you like it, in this instance, to find my du by dx, alright? So that's what I'm going to do here. This is du by dx, not dy by dx. It's du by dx because I'm just dealing with the differential of u with respect to x, but it happens to be a product in this particular case. So I'm going to try and do this on the fly. I've got my formula above, my u times my dy, v dx plus my v times du dx. So I'm just going to put the values in. In this case, for the local product, as I term it here, my u would be x cubed and my v would be cos 3x, if you look at the u term I'm using. When I differentiate my v with respect to x, differentiating cos 3x gives you minus 3 sin 3x, and differentiating x cubed then gives you the 3x squared. So that's how I get my dv dx and my du dx. I'm kind of doing this on the fly. It's like a local product application here. All I've done here is brought the cos term to the front, so I've got 3x squared times cos 3x, and I'm taking away my 3x cubed sine 3x term. I'm just doing that to put the positive term in front of the negative term as convention. So what I've done there is my sort of local product formula on du dx to find du dx. When I look at the v term and I'm differentiating v with respect to x, ln x is standard form, it differentiates to x to the minus 1. So now, I can now look at the big picture, if you like, the global product here of dy by dx, which is what I'm trying to find. So again, if I follow the formula through, u in this case, on the global u, if you like, is x cubed cos 3x. That was what I defined u as. And the differential of v with respect to x is x to the minus 1. I then add to that my v term, which I had said was ln x, and I multiply that by the differential of the u, which of course was the product, the local product of 3x squared cos 3x minus 3x cubed sine 3x. On the next line, now it's all about simplification now. All I've done here is multiply the x to the minus 1 times the x cubed to get x squared, and that's using the first law of indices. X to the 3 times x to the minus 1, you add the indice to get x squared, and then cos 3x multiplies by it, and then I add to that my ln x function as before in the previous line. Okay. All I've done on the next line is left the first term alone this time, and I brought the 3x squared outside of the bracket, because 3x squared is the highest common factor for the bracketed term. Okay, if you look at the bracket term on that second expression, 3x squared is common to both of the terms in the bracket. So I just factorised on that, and then I factorised one more time here because x squared is actually common to both of those terms now. So if you want to, you could have a dy by dx, the first differential, that's what I'm trying to find, as x squared, open bracket, cos 3x plus 3 ln x multiplied by open bracket cos 3x minus x sine 3x, close brackets. Okay, so a complicated example, that one, because you had a product within a product. But if you go back and look at the solution again, maybe step it through, hopefully you'll see the process involved. Exercise 5, last example for this presentation. This is where we're going to find the rate of change of, in this case it says voltage, by default that would be respect to time. So they've changed the variables on. Instead of having y equals some function of x, they have v for voltage equals some function of t time, and it's 5t times sine of 2t. Now what we're going to do slightly differently here is we are going to differentiate it, and it is a product, but we're then going to use the equation because we're given a condition to find the rate of change of voltage when the time is 0.2 seconds. So same approach here, it's just the symbols have changed. We've now got v's and t's instead of the usual y's and x's. So I'm going to make u, in this case, my 5t. I'm going to make v my sine 2t. I need to differentiate my u with respect to t. So differentiating 5t, if you look at your standard tables, then that leaves you with 5. Differentiating v with respect to t, in this case, sine 2t becomes 2 cos 2t from standard forms. I'm going to apply my product formula here to this expression, and obviously using the current notation, instead of dy by dx it will be dv by dt in this case. So my u is 5t, my dv by dt in this case would be 2 cos 2t, and I add to that my v term, which is the sine 2t term, and the differential of the u, which is 5. Again, slight simplification here. 5 times 2 gives you 10. So 10 cos of 2t, add 2, I just brought the 5 to the front of the expression, 5 sine 2t. Now, in the other questions, we've stopped at that position. We've not been asked to use the equation. This final exercise, part of the exercise 1, asks us to use the equation. They say, okay, now find the rate of change of voltage with respect to time when the time is 0.2 seconds. Now, notice at this level of study, we should always use radians unless told otherwise. If you're in degree mode, here you will get the wrong answer to this solution. You must be in radians, and always assume radians at this level of study unless you are told otherwise. Okay, so to find the dv by dt, all we're going to do is put the value of 0.2 for t, so it becomes 10 times t, 0.2, and then cos of 2 times t, 2 times 0.2, and then plus 5 times sine of 2 times 0.2. The rest is basically arithmetic. We're just going through working out the arithmetic here, using our cos functions here, and adding up the values to get the final answer. So the rate of change of voltage with time at an instance when time is 0.2 seconds, we're given the value of 3.789 volts per second. Okay, here are some further problems if you'd like to practice the differentiation of products. Answers are shown in the square brackets on the right hand side. Thank you for listening to this review of the differentiation of products.